Coming back, let us see today VHDL program for priority encoder and another one is floating point converter. Okay, so let us see first of all for the floating point converter. Okay, so the floating point converter here, the input having 11 bits, the output is 7 bits. The output has two parts, mantissa and exponent. Okay, so let's start with library and use, then entity declaration, entity floating point converter or floating point encoder is port of, the input number is named as B in standard logic vector 10 down to 0, that means 11 bits, the B has 11 bits. Okay, then output is a floating point number having two parts, one is mantissa consists 4 bits, so mantissa is M out standard logic vector 3 down to 0, and exponent E has 3 bits, so therefore E declaration as out standard logic vector 2 down to 0. So closing the entity floating point encoder. Okay, right, the floating point encoder has 11-bit input and a 7-bit output. The 7-bit output appears two forms, one is mantissa consisting 4 bits and another one is exponent consisting only 3 bits. Then coming to architecture body, architecture, so architecture A floating point encoder, this is architecture name, of entity name is, then begin. Okay, so process, so the program is in behavioral model, so process of input, that is B, so process begin. Now using a if statement, we are going to check from the MSB question, if B of 10 equal to 1, so the procedure of converting the floating point, fixed point number into floating point. So from the MSB question you need to check out, so where the 1 is identified, from that 1 the 4 bits are referred as mantissa, the number of bits, the rest of bits count gives the exponent. Okay, suppose if B of 10 equal to 1, then so what is mantissa? From the 10th location to 7th location is the mantissa. Okay, then what about exponent? So the 11 the rest of the bits are 7. Okay, 4 are assigned to mantissa, so the rest bits are count is 7, so that 7 is the exponent. So like that, check each and every position. Suppose if B of 9, else means B of 10 has 0. Okay, so else if B of 9 is 1, then mantissa is from 9 to 6 and exponent is 6. Okay, else if, check out B of 8 location data, if it is 1, from that point to 4 bits, that is B of 5 is the mantissa, exponent is 5. So like that, check each and every position. Okay, fourth position, then third position. Suppose in the third position is 1, so mantissa you need to add from third position, that is 3 down to 0, 4 bits. Okay, then suppose if it is 2, if in 2, so some other way you need to assign the value, already in the previous example I given. So end if, end process, end architecture name. Okay, similarly let us see the program for dual priority encoder. Okay, the purpose of dual priority encoder, it shows first two priority inputs. Okay, as usual the program start with library IEEE, then use, after that entity declaration, entity priority 2 is port, input is a 8-bit number, that is R in standard logic vector 0 to 7, then A, B out standard logic vector 2 down to 0, A for to show first priority input, B for to show second priority input. Okay, then two more signals we are using, A valid and B valid. of type buffer. Buffer means both these two acts as input and output of data type is standard logic. Okay, so that is the entity declaration. Entity declaration for a dual priority encoder. Dual priority encoder. Okay, on 8-bit data. Dual priority on 8-bit data. Okay, coming to architecture body. Architecture name of entity name is begin. So then, since the program in the behavioral model, that's why the concurrent statement is process. So process of input R and A valid, B valid, we are going to check. Okay. Then begin. So after begin, initially I am assigning the values. A value is 0, B valid also 0, A, okay, which shows the first priority, initially all zeros, B also with all zeros. Okay. Then I am using a loop statement for checking each and every location data for I in 0 to 7 loop. 0 to 7 loop. So remember here 0th location is okay, that is MSB, whereas 7th is the LSB. Okay, as per, if you take as per table. Okay, so if R of I equal to 1, if R of I means R of 0 is 1, R of 0 is 1, and valid is A valid is 0, A valid is 0, then so 1 means it has to give the priority to that bit position. Okay, priority to that bit position. So A equal to A less than equal to convert standard logic vector I comma 3. That is, that location has to be converted into binary. Okay, because here it is in the form of integer. Now the corresponding position here I value is 0. That 0 has to be converted into binary. Okay, so that value is added, I mean loaded into A. It shows the first priority input. Okay, so whenever first priority is identified, corresponding A value equal to 1. Okay, suppose if it is fails in the sense it may fail either that location value may be 0 or A value equal to 1. Okay, so in that case we need to go to check the another else if here RF and okay, so with B valid also it has to check. So the second part is helpful to know the second priority data. Okay, so in the second iteration, suppose this condition is assume initially I of 0 has 1 and A valid equal to 1. So then in the second iteration the first condition is failed because A value equal to 1. Okay, hence it goes to else part. Here R of I, that is R of 1 location data is checked. If it is 1 and B value 0 is satisfied, hence the 1 binary equivalent is loaded into the B. Okay, so like that this program checks and gives the information first priority input and second priority input. First priority input is you can observe through A, and the second priority input you can see through B. Okay, so you go through it, and if you have any doubts, take the clarification. Right. So end if, end loop, end process, end architecture name. This is the end.